This is the beginning of our second part of our series regarding remote sensing as it pertains to satellite imagery. Now, the first part, if you recall, we talked mainly about photogrammetry and its usefulness. This second half of this lecture series, we're going to pay particular attention to remote sensing in the entire context of it being referred to only satellite imagery. All right. Now, please do take note that remote sensing, one example of remote sensing is photogrammetry, which we spoke about. Okay, well, in this lecture, we're going to talk, it's just going to give you a basic history of where remote sensing was used initially and how it progressed through the different, generations. Then, why do we choose remote sensing? As we said earlier on, at the beginning of this lecture series, remote sensing is a method of capturing data without coming in contact with the particular phenomena being measured. So an aerial photograph was taken out from a distance, and it is a method of remote sensing. A satellite orbiting the Earth's surface, capturing, for example, infrared imagery to be used later on to determine the health of forested areas or vegetation, is a form of remote sensing also. Then we will look at a definition of what remote sensing is about, what is measured in terms of remote sensing images, what we measure when we capture an imagery, and then lastly look at remote sensing process. The history of remote sensing started up during the 1960s, where you may have remembered or read about the Apollo Gemini programs. It was during these times in 1960s that these programs came to being. They also had during that time Meteor satellite, and I give you some examples here. You could go ahead and do a little research on them online to find out more about them. But the first time where a digital image was captured or processed was in 1964, and that was a phenomenal experience at that time. In 1972, the launch of the Landsat 1 satellite. Landsat satellite is an American-based satellite, and its first launch was its first version of the satellite was launched in 1972. In 1972, also Skylab, which was an equatorial Earth resource satellite, and that also had a different type of sensors. Now, please know that all of these sensors do have different sensors that capture different parts of this electromagnetic spectrum, not just the visible portion of the spectrum, but ultraviolet, infrared, microwave portion. All of these are examples of different sensors being used or available on these satellites. Read the notes that I have at the bottom of this slide. It'll give you more detailed information regarding the history. Radar technology was invented during World War II, and using radar technology in that way, the system did not, the satellite did not depend upon the sun or solar energy in order to capture imagery or capture reflective energy from the Earth's surface. So a radar pulse or that can be applied during the nighttime, where it is sent out from this satellite and sent towards the Earth's surface, and that reflected energy is then captured back by the satellite. Using that technology, they were able to use radar to map areas where during nighttime, and also where areas there are thick cloud cover can be used. During the 1970s, the instrument became more readily available to non-military users. Now, prior to 1970s, a lot of the users were military users, but nowadays it's becoming much more open. It's not totally entirely open yet, but yes, there's a lot of usefulness coming out from satellite images. Some of the accuracy of these images can be millimeter accuracy in some instances, but it is not yet public domain. Infrared film was developed during the war to identify camouflage military equipment and facilities, and using infrared film they were able to map the movement of troops, and that was very useful for them. During the 1960s, you have the Earth orbiting satellites develop, where these satellites actually obtained high altitude images of the Earth's surface, and it was independent of political boundary, meaning that these satellites were such at a high altitude that they would be over different countries, and and be able to capture during that time a very good picture or image of the area being flown over. Okay, so 1960s they were able to use these Earth orbiting satellites, and it was very useful, and they mainly focused their attention to the temperate regions and tropical regions. Development of the digital electronic imaging system, where they don't have to again depend upon film again, so they were able to relay their image data back to Earth using electronic means. Earth Resource Technology Satellite, acronym ERTS-1, that's the first version. It was sent out by the US in 1972 and it's the first non-military satellite designed to collect information about the Earth's land resources. And you have to understand that this was an amazing achievement during that time, because they could not have captured the entire, large expanse areas at such a fast rate, and they can make use of this data in other applications. So this was a big achievement in 1972. ERTS was later renamed Landsat 1. So your original name of Landsat 1 was ERTS. A little thing you should remember there in terms of history. Data was received by a network of ground receiving stations around the world. These ground receiving stations are the interface to these satellites, and you had in order to use the data, you had to go through these ground receiving stations, and these ground receiving stations would post-process the data, apply the different errors, and do all of the post-processing that is required of the imagery. Some more information regarding the history, 1975 to present. We have Landsat in Landsat 2, the Landsat program, Landsat 2 in 1975, Landsat 3 in 1978, and both of them had the multispectral scanner. There's a type of sensor built with the satellite to capture different resolutions and different parts of the spectrum. And they also had the return beam Viacon (RBV), and the RBVs was typically used for capturing aerial images at such a high altitude. Landsat 4 1982 and Landsat 5 1984, they had multispectral scanners, and also during that time they had an improvement in the multispectral scanner, which was the thematic mapper. The resolutions that you get from the thematic mapper is much better than the multispectral scanner. Space Lab shuttle mission was in 1983. It contained a metric camera, so they were able to capture aerial photographs at the same time. Large format camera shuttle mission was in 94, where they were able to get large format cameras to capture large areas. Spot 1, French-based satellite in 1986. Spot 2 in 1990. You might be wondering which two satellites are most commonly used. It's here in America is normally Landsat, and its competitor is actually Spot satellite, which is, as I said before, it's a French-based satellite. Why should we use satellite and remote sensing? In this slide, I gave you some more information, some reasons why we should use them. One being, it's a source of spatial and temporal information. Spatial, we're referring to the ability to map everything, whatever is seen and what is not seen. So being able to capture the spatial aspect at the same time, put a timestamp, which is called temporal information, is very useful. And we are able to capture land surfaces, ocean, atmosphere, the extent of the north and south pole, and also in temperate regions, and other phenomena that is of interest to mankind in general. Second reason why we should use satellite and remote sensing is to monitor and develop the understanding of environment. A lot of the emphasis nowadays is on being able to preserve our natural environment, looking at ecosystems, and one of the main methods of capturing data for a large expanse area, it is through satellite imagery. For example, it is claimed that the ozone hole above New Zealand area is actually getting bigger and bigger. Now, is that true or false? How did they measure it? We did not have surveyors going out there making measurement, but what they did was actually use satellite imagery to look at the changes in the size of the ozone hole over a period of years, and it is claimed that yes, it's getting bigger and bigger. Information can be accurate. Another reason why we would use satellite remote sensing, and accuracy is relative. It's not survey grade accuracy as yet, but who knows, in the future we might get very much better high resolution imagery in the future, but it is relatively accurate given the large area that is being mapped. It is timely, meaning that we can get more or frequent images of the areas being mapped. It's consistent. It is not just the area that is of interest is captured, but also the neighboring areas. And if you overlay one with the other over different periods of time, they would actually overlay very properly, very good, sorry. And it's large in terms of the scale. It's large expanses of area that is captured. There are some also another reason why is that historical data, quite a bit of historical data from the 60s and the 70s plus, that they use some satellite imagery, as I said in the previous slide, talking about history. So we will want to be able to continue that with great improvements in the future. We want to also, another reason why is use satellite imagery is for quantitative applications. I want to be able to get data to do climate analysis, looking at changes in temperature, looking at the changes in different type of gases, changes in the land surface, and use of the effects of aerosols and other changes in weather patterns, for example, La Nina, greenhouse effect. All of these things are important issues that require data, and in order to collect the data, remote sensing is the #1 method of capturing it. There are some commercial applications, for as I said earlier on, weather applications, where I want to be able to capture the weather patterns over a period of years. Then looking at agriculture monitoring, resource management, all of that is our other usefulness of satellite remote sensing. But there are some misconceptions in terms of remote sensing, um, and I would like to identify these misconceptions. One of them being it is considered as being expensive. Now, remote sensing, depending upon the project, it can be expensive. But if we're talking about large organization, international agencies, where there is a budget and it is for the benefit of uh, mankind in general at a global level, it can be inexpensive. Now, if it's for a small project, yes, remote sensing can be expensive, and also it can be the expense is related to the accuracy of the data. If you are looking at high resolution imagery, yes, that is going to be expensive, as opposed to low resolution, it is relatively cheap. It can be a challenge to deal with or address some of the process and steps required before you can make sense of the imagery. Now, this can be, if you're technically oriented, it's very easy to follow. For example, if you want to remove the effect of cloud cover at a very high altitude, those satellites would obviously have cloud cover. Yes, there are filters in the various software that can do that. But also there are, it would require some sort of a training before you could actually make use of remote sensing data. Not directly use the image themselves is measured. The reflectance value is captured in the image, and whatever the phenomena, there is going to be a digital number associated with each pixel, and it is up to the person who's doing the processing, post-processing the data, to have to make sense of that. And also, remote sensing, sometimes, usually the case, sometimes you have to do indirect, and you have to infer. What do I mean by that? Let's say, for example, if I'm looking at mapping the spread of West Nile virus in the US, I would not have any satellite out there orbiting the Earth's surface over the US that can sense the individual mosquitoes. So what they do is indirectly they would identify using satellites the habitats of those areas, and from the habitats we would infer that it is very likely that that the mosquitoes are living in those areas. Obviously, you have to go out and verify that, but it's not directly used, and in some of the remote sensing images of the various phenomena. Definition for remote sensing is a simple one I found. It's a science of measuring the geometric, thematic properties of objects in the environment without touching them, and using various devices in space or in air to capture the data associated with that particular phenomena. Geometric means the shape of the features, the spatial relationship between other features. Thematic is that reflectance value from that particular phenomena in that is recorded to represent that phenomenon. It's a technique of collecting information from a distance. If you're going to give a definition of remote sensing, make sure that you put in this notion of collecting data from a distance. Is generally considered to be large relative to what a person can reach out and touch. So the distance is typically, quite a few thousand kilometers, from the Earth's surface. So it's a large distance. The remote sensing image is stored as a raster dataset, and raster datasets are typically, they are pixels, and these pixels would store the individual digital number for each one of the particular phenomena being captured. It represents individual areas scanned by the sensor. The smaller the pixel, easier to see the details. So smaller pixels, more detail, more memory, and more expensive. Your remote sensing system is a common characteristic in all of the satellites orbiting the Earth's surface. What I try to do here is to give a generic overview of what a remote sensing system consists of. It consists of the energy source, and that energy source is it can be active or passive. What is more common is the passive energy source, which is this energy source from the sun that shines on the Earth's surface, and the reflected energy is what is is what is sensed by the sensors. There are various platforms available. It can be unmanned. Usually, it's unmanned platform, and the platform typically would hold the solar panels that would harness the solar energy from the sun and convert that to energy so that the satellite can do what it needs to do. And of course, some satellites would have a multitude of sensors, different types that captures, for example, visible portion, ultraviolet, infrared portion of the spectrum. Some satellites, the old satellites might have a data recording system on board, but usually the data is transmitted electronically to a ground receiving station, and that follows the next aspect of what a remote sensing system consists of, which is a ground receiving station. These ground receiving stations are located throughout the Earth's surface, and it's actually organizations that does the data processing. All right, so they would georeference the image. It will apply the spherical nature of the Earth's surface, correct for all of those inaccuracies, clean up the image. Once it's done, it's then prepared for the users, which are the end users. Data acquisition involves collecting the data from the phenomena that is of interest in that application, and the data acquisition actually captures different parts of the spectrum. It can be one categorized as a visible portion of the spectrum, or near or mid-infrared portion, or it can be thermal infrared or microwave. Now let's look at the visible, near, and mid-infrared. You can have sensors that are passive, and these are sensors that typically would rely solely on the reflected energy from the sun. Or it can be active, where, for example, it generates its own energy, sends it out to the phenomena, and it's reflected back from the phenomena, and that time delay is recorded in order to create the imagery. So we can have passive or active, and it can also be applied to microwave, where we have passive and active microwave. Yes, there is microwave in the reflective energy of the sun, and it's, even though it's a small amount, there are sensors in some of the satellites that can capture or sense those small aspects of microwave. What is more common is the active microwave, microwave that are generated by the sensor, sends it out to the phenomena, is reflected back, and that energy is recorded, and the image is generated from that. We also have thermal infrared, measures the temperature of surface, and is very useful for measuring temperatures, for example, of hot bodies or ocean temperature, things like that. Now, the uses of remote sensors is a multitude. One of the common methods of use is through natural resource mapping. Forest services might want to use it in order to look at the health of forested areas. Planners might want to use it in photogrammetry, and we can use aerial photographs to create digital elevation models, things like that. Um, Other use is aircraft-based remote sensing measurements, or where we would want to measure gamma radiation for geological exploration and mapping. But altogether, our satellite-based system measures the phenomena and it changes continuously over time. It does not capture real time in terms of a real video of the phenomena, but actually gets, as it scans the entire surface, as it goes around the area of interest, it will capture at that point in time. And it covers large and accessible areas, so very useful in many applications. Other uses are weather satellites, where we would use the information from those weather satellites to determine temperature measurements of water, the surface, and at varying altitudes also. Looking at sea surface temperatures, show the position of currents and other information important for managing fisheries. For example, if I'm looking at sea surface temperatures and water current, that will determine where particular schools of fish are located, conducive areas. We could also use remote sensing in precision agriculture if we want to rotate crop, or ideal areas where particular fertilizer need to be applied for a large expansive area. And also we use digital measurements if you want to collect those sort of data at a very high speed. We can use that in terms of getting high resolution cameras and that are capable of storing or sensing high resolution images, which are useful in in terms of surveillance. What do we measure in remote sensing? We measure three entities. So it's spectral entity, which is that reflected energy from the sun. This is your phenomenon. This is the energy from the sun coming in. It is this energy that we would measure or record. Also, we measure the spatial entities, meaning the relationship of the phenomena with other features in the study area. And we also capture the temporal entities as a snapshot over a period of time. So all in all, our remote sensing image would be measuring three entities: spectral, spatial, and temporal. Now our original data from our image that is stored in our image is called digital numbers. Prior to the system converting that to digital numbers would be the radiance value, the frequency at which that reflected energy is reflected from the phenomena. Those type of values is categorized as data. Our radiance values and our digital numbers, we cannot bring any sense to it at this level. Once we take that data and put it into a model, then that model helps us to put the data into a context where it becomes information. So please note that there's a fine line between data and information. What you're seeing here is our electromagnetic spectrum, and I mentioned quite a few times a while ago that we can see. What helps us to see is the visible portion of the spectrum. Well, where is that in this diagram? Visible portion is the small part here. And because the visible portion is what we can see, we can get aerial photograph. Now, note here in our electromagnetic spectrum, there are other bands that are existing in that reflected energy. It is through the sensors on our satellites that we were able to sense those different bands and create our different layers of information. So our electromagnetic spectrum is very useful in determining or capturing reflected that we cannot see with our bare eyes, but also it also captures the visible portion. Please note that. What is remote sensing? It's considered in some instances an art, and in other instances it's considered a science. As an art, it's the development and use of analysis techniques to generate useful information. So it's an art of taking my satellite imagery and putting a model and making sense out of that for the betterment of mankind. So that's it in an when you start consider remote sensing art. It becomes a science when it provides by using the instruments and the theory to understand how the objects and the phenomena can be detected. When we start using a lot of physics and chemistry and a lot of other aspects in terms of different parts of the spectrum, we're talking about the remote sensing as a science. For example, a leaf in an open sunny area receives energy from the sun called electromagnetic energy, which is our incident energy. That energy can be divided up into three different aspects. It can be the reflected energy, which is a large majority of the energy that is sensed by our sensors on our satellites, or it can be transmitted energy, which is it passes through the surface, or it can be absorbed energy, which is used, for example, if it's leaves, it's used for photosynthesis. The process of remote sensing is shown in this diagram where, for example, let's keep it simple first of all. We have an aerial photograph, and that aerial photograph was sensed by the frame camera, which is on the base of the aircraft as it flies over the area. Now, in the background here, the same concept is applied. The satellite image was generated from our reflective energy of that particular phenomena, and it is sensed by our satellites, and that satellite converts it into a set of digital numbers. That digital numbers is then transmitted to your ground receiving station. This ground receiving station does the post processing, and that's where you get the final image used in other applications. Another diagram here shows you the incident energy. You have energy coming in from the sun. Some of it is absorbed for photosynthesis by plants. Some of it is transmitted. It goes through that particular, for example, the leaves. And some of it is reflected. As I said, a large majority of the reflected energy is what we use in remote sensing. Added on to that reflected energy is the energy emitted from the plants themselves, which collectively can add on a substantial amount to the reflected energy. So these are the energies we are looking at. On this slide, you see some examples of what are some spectral signatures of different phenomena that exist in the real world. For a forested area, we see green because the forested areas is actually, when we look at the reflectance value of a green area, forested area, this is between 0.4 and 0.8. This is the visible portion of the spectrum. Okay, now a large majority from the visible portion of the spectrum, remember the visible portion of the spectrum is what we can see. Okay, a large majority, the spike occurs in the green region of the spectrum, the visible part of the spectrum there, but a large majority of it, that reflectance value, is in the infrared. It is this infrared that we cannot see, but using the sensors we can determine the health of vegetation. So similarly, there are other signatures, spectral signatures for water, for bare earth, and for other phenomena that exist. And that's the essential concept here. Note here that everything that we see would be recorded, but also other aspects of what we cannot see but sense is also just as important. And foresters would use this part of the spectrum to determine the health of vegetation, where that's where they compute their NDVI index. Okay. Some basic physics that you would have covered already. And this is considered remote sensing as a science. Reflected energy and emitted energy is used for remote detection. So our reflected energy and the emitted energy from the plant collectively is used for remote sensing. Reflectivity is given by this formula, and it is used. These are the formula. This is a simple formula, but they are much more extensive formula that are used in the software by the ground receiving station to post-process the data. Similarly, absorptivity and transmissivity can be expressed as a ratio in terms of the incident energy, and that is another tool that is available in the post-processing software. They also consider the ground receiving station the type of reflectance. It can be specular, where incident ray angle of incident ray is equal to the angle of the reflected ray, or the energy could actually be diffuse, or it can be a mixture of specular and diffuse. Factors which determine the amount of reflective energy. You know from your physics, a black body radiates electromagnetic energy in an ideal way. If it is heated up, the total amount of reflected energy and emitted energy increases. Using this concept, we can come up with a number of surface types. A flat surface and a smooth surface, such as water or pond or pool or glass house, will exhibit a specular reflectance. Blown sand and tilled soil exhibit diffuse reflectance because that is going to be a surface that is not really smooth, so you're going to have a mixture of smooth and diffuse. All right. Most frequently in nature, example for many kinds of vegetation, there is a mixed reflectance, and that's what we have to typically deal with. Surfaces with a high specular reflectance may result in light color spots, and that's a interpretation of how the reflectance would show up on the imagery. Slope facing towards the sun will reflect more energy than slope facing away from it. So if it's towards the sun, the energy hitting the sun-facing slope will be easily reflected back into the sensors of the satellites. Steep slope facing away from the sun may be in shadow, and that's a bad thing. All right, so if you have shadows in your imagery, that imagery is actually obscuring detailed information that is not, that's a bad thing for the imagery. Remote sensing process. Let's look at it in a diagram here. It includes aerial photograph and also mid-altitude aircrafts and also our satellites. All of these different methods of acquiring data require some sort of a georeference or coordinate system. It can be in the form of pictorial data, it can be in digital format transmitted to your ground receiving station. We would use a number of interpretation tools. Alright, this includes analysis tools to produce some products. Once we have those products, we can have pie charts, bar charts, reports, maps, of course. All of this collectively will be used by the end users. So our reflective energy comes in, energy from the sun, and the reflective energy is actually sensed by these different types of equipment. And that's the remote sensing process. You know that we are making decisions here based upon what is sensed out in the real world. There is no direct contact of the phenomena. It's an example for remote sensing map. What you can see here is vegetation areas, vegetation generally. This is country area, vegetation, mainly vegetation. This is the Sahara. So ideal map in terms of showing land use, type of vegetation, type of usage of the land masses on the Earth's surface. So this was not generated from a survey or surveyors going out there to map the entire world, because that's never ever going to happen. But using satellites, we can do these sorts of things faster and, you know, relatively accurate. This is another example of remote sensing being used to map the entire Earth's surface. Note here the spherical nature of the Earth's surface, and also note the different temperatures. All right, blue, darker color blue is more, it's colder, as opposed to the tropical region, which is warmer, and the Sahara area being mapped in terms of its temperature. It also shows the temperature of the water. Very useful map if you were looking at temperature changes, global warming, things like that. So again, remote sensing is ideal for scale applications at this level of you know, global scale. It's very, very useful. Okay, we have finished with the first lecture in terms of remote sensing as applied to satellites. Please go over the material. Make sure you understand it. Download the PowerPoint presentation with the notes page and review the notes at the bottom, and we'll continue with the next lecture.